Okay, another lo-fi edition of Wait, I forgot to say the thing. Hello and welcome back to Lo-Fi Lesson 2.5. Previously we have conjectured that the opposite sides of parallelogram are congruent based on experimentation and an explanation using rigid transformations. What are we talking about? Well, that day we were spinning, we would trace a parallelogram and spin it around. And be like, opposite sides are congruent. But we didn't have proof, unless you accept proof from rigid transformation. I don't know. The book gets kind of waffly. Sometimes it accepts that as proof, and sometimes it's not proofy enough. But assuming that these are the same, mark the congruent segments. Oh, right. That's what I was doing. In the diagram, with drawing one of the diagonals of the parallelogram provided in problem 1, divide the parallelogram into two congruent triangles? Question mark. Okay, they have one. This one. One diagonal of the parallelogram provided in problem 1. Divide the parallelogram into two congruent triangles. Yes. If so, yes. Yes, so. What triangle congruence criterion, also known as a theorem, I don't know why they call them criterion. The rest of the world calls them triangle congruence theorems. Which one did we use to decide that the two triangles are congruent? I'll tell you which one we used. That matches that, that's a side match. That matches that, that's a side match. And this side matches itself, which you don't have to mark, but some people like to put a mark on it just to remind them that they know what that side is. I mean, they don't know what it is, but they know that it matches because it's the same side. It's the same line between the two triangles. So that's our third side. So it was side, side, side. Name a pair of congruent angles in the diagram provided in problem 1. Okay, this is tricky. Kind of. The easiest one is B to D. How do we know those are corresponding? Corresponding. That means matchy match. How do we know they match? They're in between the 2 and the 1 side. 2 mark, 1 side. 2 mark, 1 mark, 2 mark, 1 mark. That's the angle in between. Okay, but notice how the 1 mark is, well, actually, at least. Oh, so no reflection, just a rotation. Because look, 2 mark, 1 mark going counterclockwise. 2 mark, 1 mark going counterclockwise. So we just need to rotate this over. But that means if this is going to rotate over here. I need a new pad of paper. No time. Gotta keep going. C goes with A. Is that right? Oh, here's the problem. We need to name this BCA. So let's get this recorded before I forget. BCA, BCA, DAC. We already spoke of, angle B and D. Angle B, we don't need to triple name those because there's only one angle there. Let's get the last one. BAC. You might be saying, wait, are these the same angle, the same letters? Yeah, but look what's in the middle. C's in the middle versus A in the middle. So really we're talking about an angle over here and an angle over here. Triple mark that, triple mark this. So we're talking DCA. I sometimes forget this little angle mark. We could have also figured out, let's see, this is getting kind of messy, but between the single and the triple is our double mark angle. Between the single and the triple is our double mark angle, DAC. Yep. And between between the double and the triple. Double and triple. Bang, bang. Okay. Moving on. They correspond. Sorry, trying to do a little humor there. Identify congruent triangles and write congruency statements. Great. Launch, explore, discuss. Zach and Sion are exploring isosceles triangles, triangles in which two sides are congruent. Zach, I think every isosceles triangle has a line of symmetry that passes through the vertex point of the angle made by the two congruent sides and the midpoint of the third side. What? Okay. Isosceles. Vertex point of the angle made by the two congruent sides. And the midpoint of the third side. A line of symmetry. Is that a line of symmetry? Well, let's decide. Because this is a midpoint, this actually matches this. Zoom in. Ooh, getting weird. This is too small. Zoom out. I'm going to make a sideways one. Is that right? No, it doesn't look isosceles at all. This side. Okay, because that's a midpoint. Sometimes people label them M. M for midpoint. Do I have some more light? This looks a little reflecty. Anyway, it's an M. Alright, I can't. Alright, what about this side in the middle? Oh, once again, this side is itself. So side, side, side. So, it is a line of reflection because it's the same shape on the left and the right. Matches, it matches. But this is just one triangle, and Sion says that Zach's claim is that every isosceles. But Sion says that's a pretty big claim to say you know something about every isosceles triangle. Maybe you just haven't thought about the ones of which the claim isn't true. Maybe it's not true for some. But Zach said, I've folded lots of isosceles triangles in half. It always seems to work. Lots of isosceles triangles are not all isosceles triangles, so I'm not sure. What do you think about Zach's claim? Do you think every isosceles triangle has a line of symmetry? If so, what convinces you this is true? If not, what concerns do you have about his statement? Well, actually, we already proved it in that little. You can take an isosceles triangle of any measurements. This actually stands for all isosceles triangles. Why? Because I'm just saying that these sides match and these angles match. That's the definition of an isosceles. And then when he says take this vertex and this midpoint, at the point where you can find this midpoint, which we can because we can perpendicularly bisect things, then we know we've split this. And now we don't even need side, side, side. We could use side, angle, side. So what else would Zach need to know about the crease line in order to know there's a line of symmetry? It needs to be in between all points of reflection. What else does he need? Okay, I looked it up, and they're saying that Zach would need to know that if he's folding it. When does it ever say that he's folding these things? He says he folds it. This would have to be a 90. He'd have to know that because this line crosses the line of reflection, and any line that crosses the line of reflection has to be meeting it at a. If it wants to land back on itself, the only way this line will land on itself is if it's meeting it at a 90. Okay. But I jumped the gun a little bit because I said that all isosceles triangles have these congruent angles at their bottom corners. We actually haven't discovered that yet. So we do need the SSS. But here's what, once we have it by SSS, we then get to use CPCTC. Okay. What does that mean? Well, once we know that these two triangles are congruent, let's label it. A, B, C, M. So triangle CMB, cosmic microwave background, and triangle CMA are congruent. Now we know that by SSS. It's our proof. And then once we know that they're congruent, we can say things like, well, the corresponding angles are congruent. Corresponding angles are congruent by CPCTC. That's, you took vocab on that. That's corresponding parts of congruent triangles are congruent. So we can say things like angle B is congruent to angle A because of that. So now we know that the base angles of all isosceles triangles are congruent. Yeah, we talked about the line of reflection has to be perpendicular to any line that wants to fold back on itself. Sion thinks Zach's crease line is created to... Yeah, we already did this. We are ahead of them. If two triangles created by the folding of sides of the triangle in half are congruent, what does this imply about the base angles? Done already. If two triangles created by folding of sides of the triangle in half are congruent, what does that imply about the crease line? What? Oh, this is really fun. We'll actually do this one because we discussed how a straight angle has 180 degrees. So the measure of angle AMB equals 180 degrees. This is a straight line. But we also know, because we know angle CM is congruent with angle CMA. Hey, now that I'm doing this, I realize when I did the base angles, I screwed them up. They should have been they should have been CAM and KABIM. They should have been CAM and CBM. I did CMB and CMA, which is what I want to do now because these two are equal. Okay. But because we know angle addition, if we add them together, we will get 180. What am I doing here? CMB plus angle, measures. These are measures. Measures angle CMA equals 180 degrees. What am I going to do here? Okay, now because they're congruent, I know that their measures, if I change these to measures and get rid of the congruency symbol, I'm actually going to swap. I'll swap this one out. It's going to be swapped for the measure of angle CMB because the measure of angle CMA equals the measure of CMB. They're the same. How do we know? Because they're incongruent triangles. We know because triangle CMB is congruent to triangle CMA. They're congruent triangles, so we know those angles match. If we know those angles match, I can swap this one out for that one. And now I have two CMBs equal 180, which means I have two measures of angle CMB equal to 180, which means I can now do algebra and get measure of CMB. We know the measure of CMB is 90 degrees. Yeah! We proved that this is a 90, and that means that is a 90 as well. So from the vertex to a midpoint in an isosceles is 90 degrees. Forms a 90-degree angle with the base. Okay, for part 2, you're going to pick one, draw it, or construct it. So probably the rhombus is the easiest to construct because you don't need a right angle. Construct it. Then draw its diagonals. Label. Then make a really nice and then based on your drawing and the fact that all four sides are the same, if you do the rhombus, based on 1, the drawing, 2, what you know about the rhombus, and 3, information about the sides and angles that you can gather based on the lines of reflection and rotational symmetry, list as many pairs of congruent triangles as you can. So your rhombus, I'm just going to sketch one. It's going to have a bunch of triangles in it, including ones that overlap 2 triangles. Find the congruent ones. For each pair of congruent triangles that you list, state the criterion you used. How do you know they're congruent? Is it because you were able to figure out their angles are that 2 angles must be the same in a side, 2 sides in an angle, or you found 3 pairs of sides that match in the diagram. And then state the congruencies that let you claim the ASA or SAS or SSS. Man, that's a lot. That's so confusing. I wish there was a table that we could use. Yeah, so out of your rhombus with its diagonals, I'm assuming you're going to make, maybe make does that? Let's try a more extreme rhombus. Let's see better. Are all 4 of these the same? No, try to prove it. Try to prove that all 4 of these are the same. Is this one match this one? We know. Do we know that these angles are the same? Try to work your way around. And once you find a triangle, you can say this triangle is congruent to this triangle. Based on this, well, if it's side, 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 there better be 3 pairs of sides. There's a pair of sides, there's a pair of sides, there's a pair of sides. So I can use SSS. Okay. That should take an extra 15 minutes. Also, don't upload this page. Just show it to me. I would like to see what you found. And, have a growth mindset. Whatever you're able to do with it, however far you get. Just show me when you feel like you're done, or you filled out the table, or you got 1 or 2 and you feel like you can't find any more. Alright. Oh, are we gonna make it to 20 minutes? Is this gonna be the first 20-minute video of the year? Nah.